Welcome to Energy Management, a small system approach. Providing wastewater and drinking water to the citizens of your state requires a significant use of energy on a daily basis. Energy management has become one of the most significant issues facing wastewater and water utilities today, with their water and wastewater utility consumption responsible for 30 to 60% of their energy bill. This training program is geared specifically toward practitioners and trainers in the water and wastewater field who, with the working knowledge of their treatment plants, can deliver training on energy conservation. This training program, Energy Management, a Small System Approach, was developed by the Maryland Center for Environmental Training of the College of Southern Maryland and funded by the Maryland Department of the Environment through their fiscal year 2016 Performance Partnership Grant, Water Pollution Control Activities with the U.S. Environmental Protection Agency. MSET's technical assistance providers have a significant amount of experience providing on-site, over-the-shoulder technical assistance to small to medium systems in Maryland. MSET recognizes the challenges faced by smaller utilities and developed this training with that in mind. This outreach is an attempt to bring energy management to those systems in a practical manner. Energy Management, a Small System Approach. Providing wastewater and drinking water to the citizens of your state requires a significant use of energy on a daily basis. Energy costs are steadily rising. Energy management has become one of the most significant issues facing wastewater and water utilities today, with their water and wastewater utility consumption responsible for 30 to 60% of their energy bill. This course will provide superintendents, town managers, and municipal officials with a step-by-step methodology to identify, implement, measure, and improve energy efficiency at their wastewater treatment utilities. Specifically, this course will look at the processes, at what each device does, and determine how some energy costs may be reduced by controlling the process and equipment. Participants are going to review reducing energy costs and some limitations they may encounter in the process. In addition to discussing ways of trying to save energy, they are also going to review details related to their tariff and electric bills. This is very important because there are a lot of opportunities for minor changes without investing large amounts of money that they might be able to implement simply by understanding how they are being charged. They will review specific wastewater treatment processes and associated pieces of equipment. We are going to talk more about these processes and why there are some limitations to the measures we can take, especially for wastewater treatment plants moving from biological nutrient removal, or BNR, to enhanced nutrient removal, or ENR. For example, it's not just a matter of turning the blowers off for a while to save energy. With the newer ENR plants with a lot more complex equipment, some of the town officials have sticker shock when they see their first electric bill, especially when they recently upgraded from a plant that was possibly a lagoon or trickling filter to ENR, or where towns have gone directly to ENR. So remembering that our primary function is to be in compliance with state and federal regulations, regulations relating to our MPDS permit and the Safe Drinking Water Act, we can review measures we can implement to conserve energy. Obviously, we have to look at our permits first, before we can start looking at energy conservation. We are also going to discuss how to implement and monitor the progress of an energy conservation program. Upon completion of this training, participants should be able to 1. Describe and understand basic electrical terminology. 2. Read and interpret a utility electric tariff. 3. Understand how to organize your conservation effort. 4. Know how to determine your present energy consumption and how to conduct a survey of specific equipment and processes. 5. Evaluate potential energy conservation measures, or ECMs. And 6. Discuss how to implement and monitor your progress and success. The goal is to discuss what are considered reasonable ways to try to save some energy for this industry. By organizing a conservation effort and by learning more about the energy conservation opportunities of the different types of equipment. Furthermore, we will discuss how to evaluate what changes can be made to save energy and review energy conservation measures, or ECMs. Course Agenda. This training course has 5 training modules. Number 1. Energy Conservation. Small wastewater treatment plants, biological processes. Number 2. Definitions, formulas, and basic concepts. Number 3. The Energy Management Plan. Number 4. Performing an audit and assessing data. Number 5. Process and Equipment, ECMs. Energy Conservation. The small wastewater treatment plants, biological processes. This section discusses the current state of small wastewater treatment plants and the biological processes seen most often in the state of Maryland. We are going to look at the energy cycle and how power is used to move and treat water. We will discuss the biological processes, permits, and technology, and what we have to watch carefully for as we implement energy conservation methods. The energy cycle. When talking about the energy cycle for water and wastewater systems, start at the water source. The source of the drinking water may be groundwater or surface water. The next component of the cycle would generally be some sort of treatment, which could range from a complete surface water treatment plant to just a well with a chlorinator. Regardless, a certain amount of energy will still be required to operate the facility. So start with the water source, and from there we have water treatment. Next, water is pumped into the distribution system. There might be intermediate pumping stations in the distribution system used to get the water to a higher elevation or different pressure zone. Water is then supplied to homes and businesses throughout the system. The wastewater generated by these consumers then enters the collection system that delivers it to the wastewater treatment facility. In order to get this wastewater to the treatment facility, most collection systems include pump stations at appropriate locations, which of course are significant energy users. This energy cycle therefore includes all of the above components that consume energy and are opportunities to reduce energy consumption. In Maryland, many of the wastewater treatment plants are at the limits of technology. This new technology involves a lot more controls and a lot more equipment. The challenge is how is this managed while trying to save energy and not jeopardizing compliance with the NPDES permit. Energy conservation and biological process. For those smaller wastewater treatment plants that are essentially activated sludge facilities, a key component in terms of making those plants operate properly is providing adequate aeration. Aeration is provided by blowers, which are generally run continuously in order to ensure adequate treatment. The BNR and ENR plants are now going a step beyond the basic activated sludge process since they require nitrogen removal and phosphorus removal. With higher levels of treatment, there is additional quantities of waste sludge generated that must be accounted for. This provides another area of increased energy use that has to be considered. This is the definition of total nitrogen. The ENR permits have a yearly limit or cap based on total nitrogen and total phosphorus. The BNR plants in Maryland, for example, permits require meeting a total nitrogen of 8 mg per liter. The new ENR permits in Maryland are based on yearly caps of pounds per year. That is based on total nitrogen of 4 mg per liter. This is really tight as a state policy and is probably the strictest limit found anywhere in the country at this time. These ENR permit limits are at the limits of technology. This needs to be emphasized because if adjustments are made to save energy, it is important to keep in mind the permit limits the plant has and what kind of performance that has to be maintained at your treatment plant. The first step in reducing total nitrogen is nitrification. It is converting the ammonia nitrogen to nitrate nitrogen. This requires aerobic conditions. In order to take the first step in reducing nitrogen, we have to have aerobic conditions to convert ammonia to nitrate. How do we get aerobic conditions? What piece of equipment is critical for aerobic conditions? Blowers. Blowers are obviously one of the big energy users. Dissolved oxygen levels in the aerobic zone should normally be somewhere in the 2 mg per liter to 4 mg per liter range. This is an example of what a plant might look like when providing aeration in order to maintain dissolved oxygen throughout the whole plant. When a plant like this oxidation ditch is aerating continuously, it will be reducing BOD as well as nitrifying. This is a large basin using a lot of air. There would be large-sized blowers using a lot of energy in order to do this. The next step is denitrification. This occurs when the nitrate is converted to the nitrogen gas that is released into the atmosphere. This is how a plant meets the total nitrogen level. This denitrification process has to be done under anoxic conditions. Anoxic conditions means no dissolved oxygen or DO, or the minimal DO possible. The closer to zero, the better. So there first was one process, nitrification, where air is needed and dissolved oxygen, and then the second part of the treatment process where there cannot be any dissolved oxygen. This is where balancing can become complicated. In order to meet that total nitrogen, the air volume and dissolved oxygen concentration must typically be in the 2 to 4 milligrams per liter range in the aerobic stage, but be near 0 milligrams per liter in the subsequent anoxic stage. To do this, the air cannot be turned down completely to get anoxic conditions, because if the air is turned down too much, there will not be enough air provided to convert the ammonia to nitrate. Nitrification will be incomplete. That is why it becomes a balancing act when trying to consider energy conservation, while at the same time making sure meeting the permit limits are not jeopardized. This is an old slide of the Western Branch plant, which was one of the first plants in Maryland that went through a full upgrade for B&R at that time. Now they are an E&R plant. They still have essentially the same 3 stages. They have aerobic conditions to reduce the biological oxygen demand, or BOD, first using aeration tanks and clarifiers. Then they have additional aeration for nitrification, converting ammonia to nitrate. Then, once they have done that, they have to get rid of the nitrate, so they go into anoxic conditions where denitrification occurs. In order to do that, they have to add an external carbon source like methanol, because the carbon source that is coming into the plant, BOD, is gone by the time that they get to the end of nitrification. Because most of the BOD or food is consumed in the first stage, an external carbon source, such as methanol, is added to provide the denitrifiers the food source they need to reduce the nitrates to nitrogen gas. Now, those who have E&R plants right now might be saying, "My plant is not like that." And that is true because the technology has evolved over the years. With this design, there were 3 discrete sections of the plant where air could be controlled. In the first section, there was enough to get the BOD removal. Then you can control the aeration in the second section to make sure that you convert the ammonia to nitrate. And then you have another discrete section of the plant where you create an anoxic zone for breaking down the nitrate. In the modified Ludzak-Edinger, or MLE, process, there is one basin typically with baffles to separate anoxic zones and aerobic zones in the same basin. It is not like the baffle actually separates the basin, where there is a discrete area with one type of bugs and another discrete area with another type of bugs. The same microorganisms exist throughout the basin. The operator manipulates the environment in different sections of the basin to favor nitrification in the aerobic zone and denitrification in the anoxic. Within the same basin, we are trying to do the same things that the previous schematic showed in discrete sections. Nitrify in one section, denitrify in the other section. Here, the nitrifying and denitrifying is in one large basin, so here is where the balancing act comes in. We do not want any DO in the anoxic zone, but we do want DO in the aerobic zone. And we are returning solids from the aerobic zone back into the anoxic zone, which means we are recycling DO to the anoxic zone. If we are trying to save energy, we can reduce the air in the aerobic zone, so we will be recycling less DO to the anoxic zone, which will help with denitrification. This is good because we want to reduce the air, because maybe we are returning too much dissolved oxygen in the anoxic zone, and it is interfering with denitrification with breaking down the nitrate. But if we turn the air down too much in the aerobic zone, what can happen? We may start to lose nitrification. If we don't convert that ammonia to nitrate, the rest of the process falls apart. We can't lose nitrification. Okay, so maybe we can try to reduce the air. But it's not that simple when we are dealing with a BNR or ENR wastewater treatment plant. What are the consequences of inadequate air and excessive air? Inadequate volumes of air will result in incomplete nitrification and high total nitrogen in the effluent. Excessive volumes of air will result in DO recycle that will inhibit denitrification and result in high total nitrogen in the effluent. Here is a treatment plant where the biological makeup of this biomass is the same all the way through, but parts of this basin are not aerated and parts are aerated. So within the same basin, there is nitrifying in the zones where the air is on, and there is denitrifying in the zones where the air is off. This cycles every 30 to 40 minutes, where the air switches from the first 3 chains to the second 3 chains. When trying to do these two process functions in the same basin, and also balancing that with energy conservation measures, these 3 goals become a complex balancing act. What are some of the things we can do in the treatment system to help us to add the right amount of air? We know this is not an exact science. If we are trying to save energy, what are some tools that might be available that can help us to fine-tune the amount of air and how much air we are adding in one of these processes? What are some of the key factors in these plants and the design of these plants to help us make the right decisions? A key parameter to keep an eye on is the ammonia levels. Generally, operators collect samples and run them on their test equipment, or send them to an outside lab to make sure the ammonia is low. Now, there are reliable probes for both ammonia and nitrate that plant operators are starting to use. In the past, these probes were not very reliable, but they are getting a lot better. We have ammonia probes, we have nitrate probes, and DO probes, which have been around and relied on for ages. An ENR plant should have at a minimum a good DO control system and DO probes that are reliable and accurate. The DO probe can be used to control the speed of the blower, inlet valve position, and even turn blowers off periodically when the DO gets high. These are good energy conservation measures. The DO probes are not that costly, but when we get into using the ammonia and nitrate probes, it can become expensive. So now it comes down to the point where we have the DO probes, we have the DO control system, we are doing good controlling the amount of air, and can try to conserve energy. If we go to the next step with ammonia and nitrate probes, maybe we can even fine-tune that even more. But these probes cost $15,000 to $20,000. Can the savings outweigh the cost? Now we have to justify how much energy can be saved by investing in ammonia and nitrate probes to fine-tune the amount of air that we are supplying and what is the payback time. So looking at measures like that, we can invest money to save energy. But is it cost effective? It is not that simple to say, okay, just turn the air up and down, because the processes are changing all day long. The flow is changing, the temperature is changing, and DO control is absolutely necessary in any BNR and ENR plant. The newer technology uses feedback control where we have DO probes and ammonia probes working in conjunction to send signals to the process control system that could help control the amount of air we are adding. This is a 4-stage Bardenpho plant, where first there is anoxic, then aerobic, then anoxic, then aerobic. This is what a four-stage Bardenpho plant looks like. This plant has an anoxic zone where they do not want DO, followed by an aerobic zone where they do want DO. Then there is another anoxic zone, followed by another aerobic zone in the back end. With each of these zones, it is not like these baffle walls are completely separating one zone from the next. The flow is going around and underneath. There are openings in these baffle walls, and so managing the amount of air they put in is going to affect how well they nitrify and denitrify in the same basin. They also have DO probes, but they do not have ammonia and nitrate probes. When there are DO probes, they must decide where to put them, making sure they have good probes that are reliable. They must check them by calibrating them regularly. These design issues are absolutely critical to ensure they accomplish goal number 1, which is to meet their permit. Then goal number 2 is to try to do it as efficiently and cost effectively as they possibly can. Biological phosphorus removal in plants like a 5-stage Bardenpho process includes an anaerobic zone for enhanced biological phosphorus removal. But there are still aerobic zones to ensure efficient biological phosphorus removal. Most of your plants are probably using chemical feed systems. One of the things seen in most of the plants are the chemical feed systems used for phosphorus removal, whether we are adding chemicals like alum, ferric, etc. These systems are often not designed to use energy efficiently. We have chemical feed pumps that are pumping chemicals into areas of poor mixing. If you talk to someone who knows a lot about chemistry, or your chemical representative, they will tell you that when feeding any chemical, it is critical to get good mixing at the point of application. We can really save on chemicals. We can save some money if we can turn down our chemical feed. Even though they do not use a lot of energy, they run all the time. The larger the plant, the more chemicals we are adding, the more we are potentially able to save. If we can save money on chemicals, we can possibly use that money for some of the other energy conservation measures we will talk about. Most of the plant's waste sludge is put into a holding tank where they aerate it. In the case of large plants, they typically have an anaerobic digester. Most plants typically dewater and haul the dewatered sludge. If there is an aerobic digestion, there are blowers typically ran continuously day in and day out using a lot of energy. We worked on this years ago because we found when we aerated continuously that we actually were nitrifying in the sludge basin. And when we turned the air off to decant, we saw spikes of nitrate in the decant going back into the plant. So by putting timers on the air supply to the sludge holding tank and turning air on and off in cycles, we could actually nitrify and denitrify in the sludge holding tank, and thereby reduce the amount of nitrate recycled back to the process. What this accomplished was we cut the time the blower was on in half. Instead of running 24 hours a day, it was only running 12 hours a day, and that saved a lot of energy. Then when we did decant, or when we ran sludge through the belt filter press, the filtrate or the decant was a much better quality than it was even when we were aerating continuously. So there are things you can do. By investing in timers, for example on blowers that do not have to be on all the time, can save a lot of energy. Let's talk about saving energy. We want to talk about specific equipment, but we have to understand that our number one priority is always going to be meeting these stringent nitrogen and phosphorus limits. So we have to balance that with trying to save energy. This won't be easy all of the time. We have done energy audits in the ENR plants in Maryland, and we found that their tight limits put a limit on how much we could do as far as energy conservation.